Oh my God. Now I'm going to make up another thing. This is not something that is ever written down this way, but I'll call it the hydrostatic law. It's basically a law you can use, to solve problems. Okay, so this is I'm going to trademark that, the hydrostatic law. And here it is. Pressure will be the same along a horizontal line. If you just apply this, it's the key to all the static problems. Along a horizontal line. And now here come the caveats. Are you ready? Through any, okay, no, that's not the caveat. Through any, and here's the caveat, single, continuous fluid. Okay? So by that we mean single means only one density. If you have two fluids, different densities mixed together, we'll do that later. Right now it just means it's a single fluid and it's completely connected to itself. It's not like there's some fluid over here and some fluid over here. Okay, it's all one flow of fluid. So we're going to draw a bunch of geometries to give you an idea. Somebody's asking, will this always be given? No, it won't always be given. Sometimes we'll give you this, and you have to solve for that. Oh my God. But you'll always have enough information to solve the problem, unless we mess up, and that never happens. When will the Chapter 9 and 10 book questions be posted? Oh, they're coming. They're coming, because we know you want to study for the exam. Okay, so we're going to draw a bunch of cases, and we're going to apply this law and see what it tells us. Okay, so let's draw this. Here we go. Get ready to get your drawing ready. All right, so here is like a beaker, and it's connected to a bigger beaker. Right, and there's some water here, and there's some water here, like that. That's all you know, right? And we have its atmospheric pressure on both sides. Right? First you could ask, is that even going to be stable? Because you got more weight on the right side than the left side. So it seems like, will the water flow, and because this one is bigger? No. This is stable. This is fine. So the bigger area doesn't matter. It's still true. Let's draw some horizontal lines. What's the pressure here? Atmospheric pressure. Because I drew a line right where the atmosphere is. What's the pressure here? All along there, the pressure is P atmosphere plus D, rho G D. Right? I just used the hydrostatic equation. That means the pressure here is P atmosphere plus rho GD. The pressure here is P atmosphere plus rho GD. The pressure here is P atmosphere plus rho GD. Okay? So if it's the same on both sides of the tube, does any water flow through the tube? No. What's the net force on this chunk of water in the x direction? 0. It's being pushed by P atmosphere plus rho GD this way and P atmosphere plus rho GD that way. So this thing just sits there. Even though this water is heavier than this water, right? This is not pushing, even though it's heavier, it's not pushing harder because it's the same area here. Right? So it balances. So that's totally stable. What if we did this? What if we had this? Oh, now what if we went and did that? Don't do it. Oh, I'm going to do it like that. What would that do? See, because now the area is changing. The pressure here is bigger than here because the area is bigger. No, it's not. It's just going to do this. Right? What's the pressure here? P atmosphere. What's the pressure here? I don't know. But it's the same here and here. Right? That's what the hydrostatic law tells you. If you say, oh, that's D deep, do we have to be right on the tube for that to work? No. It's true anywhere. It's not just at interfaces and just at tubes. It's true anywhere. Here it's P atmospheric plus rho GD. Right? Any weird scenario we give you, if it's not flowing and it's a single liquid and it's all connected to itself, this will be true. Let's see if we can make it confusing. Okay, what if we have two weird shapes and a weird connector? Happened to me the other day. It's okay. Happens to everybody. There's a weird shape and the connector does this. Oh my God. Surely that didn't happen. Yep. Happened. I got to a doctor though, and it goes like that. What's that going to do? Oh my God. Is this going to push it down? No. It'll be also ATM. Atmosphere here, atmosphere here. The little levels will be the same. We could ask, what's the pressure here? Anybody want to shout it out? Yes. PATM. What's the pressure here in the tube? But it's below these. Oh, well, if this is D, it's just PATM plus rho GD. It doesn't matter if it's in the tube or the top of the tube or the bottom of the tube. What's the pressure here? That's PATM plus rho GH. All right, some little drop. Okay. So the pressure slowly increases as you go farther down. Right? That's all it is. Let's see if that's really true. I forgot to prove that's true. Here is a thing of water, and I put 3 holes in it. And there they go. Oh, one got blocked with tape in my dramatic. Oh, no, I got to take this off. There we go. Oh, this is messy. My bucket's not big enough. But you can see, oh, hell, let's just pick it up, right? So you can see the top one isn't shooting out very far, is it? No. And the bottom one's shooting out really far because it's, got the higher pressure because it's lower. See, rho GD. As D gets bigger, I'm going to make a mess. This is my favorite demo because I can eat it. I hope I've changed that to water because it was 200 proof ethanol before. Oh no, now we're good. Okay, when y'all leave, seriously, don't slip. Okay, I need you to keep moving that way, okay? No, you don't have to, I'll do it. Okay, so it keeps going. Okay, that's really not a good sound while I'm lecturing. I really need that to stop. Okay, let me get rid of this. This is too stupid. Even for me, this is like, well, then I'll get it wet and somebody will fall. I just don't know what to do. This is a new demo. I have to listen to it. Okay. Reminds me of a urologist visit. Okay, what if we do this? Oh my God, don't do it. Oh, I'm going to do it. What if we tilt one? Are you kidding me? What if we tilt one? Is this going to do that? No. It's going to do this. PATM. All right? What's the pressure here? Right? PATM plus rho GD. Right? The geometry of the container doesn't matter at all. All that matters is the height that it comes down. Turn the bottle on its side. Oh, here's an idea. I can do that. Hey, I'm an experimental physicist. Thank you very much. Okay. Oh, God, that was that. Okay, it's like this whole lecture is like too many noises. Okay. Okay, so the main thing to learn from this is that you can always, if you have atmospheric pressure, you always have a reference. And you can get the pressure at any depth just by the surface pressure plus rho GD. Okay, that's the basic law. Okay, so now we're going to do a few sample problems, like things we might ask you.